In the lab, we make practical use of the change in vapor pressure with temperature with a tool called a rotovap. This is a tool that we use for distillation, for purification. So you would put a sample that you want to purify down in this container, and then there would be something like an oil bath or a water bath down here to start heating it up. As you heat it up, some of it's going to evaporate, and we're going to connect it through this apparatus over here to a vacuum pump. If we connect it to a vacuum pump, we're going to reduce the pressure inside of our setup, and as those molecules evaporate, they're going to work their way through over to this part of the apparatus, which is a water-cooled condenser. They're going to the gas-phase molecules will condense, and then they will drip down into this receiving flask. And so basically the idea is if you have some junk dissolved in your solvent and you take it through this process, the junk stays behind in this flask, and what you end up with over in the receiving flask is going to be much purer. And for high boiling solvents, it can be really hard to purify them by distillation because you have to get the solvent heated to such a high temperature. But if you can pull vacuum on it, you reduce the applied pressure, and so it'll boil at a lower temperature by those vapor pressure curves, and you're able to purify your high molar mass solvents this way. Another issue I wanted to wrap here into our discussion of vapor pressure is the concept of curve fitting. We'll find often in science when we take data about two different variables and we plot them that we get some sort of regular curve shape. If you look at these vapor pressure curves, they all look like they have the same general shape. They are modified from one another, maybe by some sort of multiplicative constant, but they all have that same overall curve. As you go to higher temperatures, the vapor pressure goes up, and it all seems to go up in a similar fashion. So when we see something like this, historically, we try to analyze it. In the days before calculators and computers, that sort of curve analysis would be kind of hard to do, but doing analysis of lines was much simpler. And so scientists would work to somehow mathematically convert the data into some sort of a form that when they plotted it resulted in lines. And one of the things that we often found with this sort of analysis is that once you got a line, the slope of the line would have some meaning associated with it. You're going to do this repeatedly in the 1142 lab. If you're taking that this semester, there's a Beer's law experiment that you will do where the slope of the line gives you information about the molar absorptivity of the compound. We use that again in the crystal violet lab. There are a number of labs that you'll do where you'll have to do some sort of curve fitting to linearize your data. For our vapor pressure curves, the way that it gets linearized is a little bit complicated. So let's look at the next slide. It turns out if you're going to turn the pressure and temperature data into a line for vapor pressure, you've got to do some weird stuff. Instead of plotting the pressure on the vertical axis, we're going to plot the natural log of the pressure, and instead of plotting the temperature, we're going to plot the reciprocal of the temperature. So literally, if you were to look at the data analysis on this, if you collected pressure and temperature data, what so you're just, doing your plot here where you're collecting data points for all of these. The way that we can turn this data into a line is to do some math on our data. So you would use your calculator, and whatever you had for pressure, you would run that through your calculator and calculate what the natural log of the pressure was, and whatever you got for temperature, you'd run that through your calculator and you would calculate the reciprocal of those temperatures. Then you're going to plot that, and this 1 over temperature column becomes your X data point, and so I'm going to put X up there in parentheses, and the natural log data becomes your Y data point. And so if we rearrange this curve, or the equation for this line a little bit, we're going to get Y for our natural log of the vapor pressure. X is the 1 over temperature. This whole expression here becomes the slope, and then this constant gives us the y-intercept. So the slope of this plot is related to the delta H of vaporization of your substance. So this gives us an experimental technique to calculate the delta H of vaporization. Once you do this linearization and you get a number for the slope, that slope is equal to minus delta H of vaporization over R, the ideal gas law constant, and so you can rearrange that to solve for the delta H of vaporization. All right, let's look at the next slide. All right, we're going to wrap up our discussion of vapor pressure with a couple of clicker questions. This says that Bobcat is going to put a small amount of water into 4 different Erlenmeyer flasks, seal them up with a stopper, and set them aside. After a day, all of them looked like the flask at the very beginning of this presentation, where there was still a small amount of water on the bottom, and there's definitely condensation on the sides. So the question I'm posing is, which one of these flasks had the greatest partial pressure of water vapor? Now, stop this video for a moment, think about this, and then we'll go through what the answer is. All right, hopefully you actually stopped the video and thought about this. We have 4 different sizes of flasks, ranging from little at 25 mils to 10 times bigger at 250 mils. The key to answering this question is recognizing that vapor pressure is an intensive property. An intensive property is something that is the same whether you have a little bit of the sample or whether you have a whole lot. Probably the first example of an intensive property you look at in chemistry is density. It doesn't matter if you've got a couple of drops of water or if you've got a bathtub full of water. The density of the water is 1 gram per mil. Well, it turns out vapor pressure is the same thing, because that amount of water that will go into the gas phase is, in terms of its pressure, is a fixed amount. Once it has reached equilibrium and you've reached that vapor pressure, it's the same, whether you give it a great big volume to occupy or whether you give it a little itty bitty volume to occupy. So the vapor pressure of water, it remains the same whether you've got a little sample of it or a big. So the best answer would be 5, that they all had the same partial pressure of water. Now what will change this is if you change the temperature. So if we had 4 different flasks that were at different temperatures, the highest temperature flask would have the highest vapor pressure, but that's not the case here. Here we're assuming they're all at the same. So let me just put a little note up here. But vapor pressure will change with temperature. Okay, so giving it different volumes to occupy, the vapor pressure will be the same in all of them. But if you start heating up one of these flasks, it's going to have a higher vapor pressure. All right, let's take a look at one more clicker question. This is almost the same question, except now instead of looking at vapor pressure, we're looking at mass. Which one of these flasks would have the greatest mass of water vapor pressure, of water vapor present. They all have the same vapor pressure, but what we have is 4 different flasks ranging from little at 25 mils up to great big, 10 times bigger at 250 mils. And oh, those are terrible drawings. But this one is 25 mils, and this one is a 250 mil flask. The vapor pressure in both of these is the same. But, oh, and so you should probably pause and work your way through this. All right, let's assume you've paused, you've thought about this. Hopefully the conclusion you reached was that the 250 milliliter flask has the greatest mass. The partial pressure of water in each one of these flasks is the same, but the 250 milliliter flask has a bigger volume. Having a bigger volume, we're going to have more water molecules in it to exert that same vapor pressure. The mass is an extensive property, so if we have a bigger amount of water in the vapor pressure, in the vapor phase, it's going to have a greater mass. So mass is an extensive property. It would be the same answer if I asked which of these flasks had the greatest volume of water vapor, right? Because we're assuming that there's just a little bit of liquid water on the bottom of each of these flasks, so the vast majority of the flask is filled with the vapor phase. So the biggest flask would have the greatest volume, and the biggest flask would have the greatest mass of water in the vapor phase.